Swayam Prabha. Digital India. Educated India.
In this session, we'll be learning how to model in Simulink. Okay, just for the understanding, how many of you know what Simulink is? Please raise your hand. You know? Okay. So, for those who don't know, Simulink is again a modeling background where you can model your system using block diagrams. Okay, so if that actually gives you a like block understanding of how the system is. There are different blocks in the Simulink for different operations. Okay, like for integration you will have one block. For product like multiplication you will have block. For addition, for every operation you will have a block. So you'll just have to make a block diagram. It's more like a logic circuit. Okay, so if you have a better understanding of logic circuits or block diagrams rather than the mathematical expression, Simulink is something you can look for it. Okay, so in the last session we simulated this Duffing oscillator. Now I think everyone is familiar with Duffing oscillator. It's a nonlinear system with cubic stiffness nonlinearity. Okay, so just for a better understanding for Simulink, we'll be simulating the same system using Simulink. I hope now everyone has those MATLAB codes. It's been shared with you and everyone would have gone through it once for understanding. So I'll start with like I'll just consider it as a fact that everyone knows about Duffing oscillator, and like in this session we will just understand how things are modeled in Simulink and how you can save your model in workspace of MATLAB. So Simulink is just a MATLAB add-in. Okay, I'm not sure whether you can use it separately or not. Like it might be, I'm not very sure about it. But if you have a MATLAB, you can install Simulink as an add-in and you can use it. Okay, and you can run some like even you can make, if you are comfortable with MATLAB codes, using MATLAB codes also you can make blocks in Simulink. That is also possible, but that you can take later on if you are interested in. Today we will be just modeling Duffing oscillator in Simulink. Okay, so I'll just give a brief about how it is going to be, give an idea, then we'll start modeling it. Okay, so your Duffing oscillator is x double dot plus gamma x dot plus alpha x plus beta x cube is equal to delta cos omega t or sin omega t, anything you can take. It's just sinusoidal force that you want to take. Okay, it can be delta cos omega t or delta sin omega t. Just needs to be harmonic. Like we are considering harmonic force. Okay. Okay. So even in MATLAB, what we did, we just segregated this part of equation separately, right? Like the highest order we have to take on one side, and we have to keep in mind, like integrating x double dot you will get x dot, integrating x dot you can get x. So we can use an operator integration on x double dot and get x dot. Again we can integrate and get x, right? That idea should be there in mind. So for that, your x double dot, what does it become? Your x double dot is minus gamma x dot plus alpha x plus minus alpha x minus beta x cube plus delta say sin omega t. Okay, right? Now we will see, we will try to design roughly first how the block diagram should look, and then we can model it in Simulink as well. Okay. Okay. So you can see here I have to add everything, right? It is basically adding of minus gamma x dot, adding of minus alpha x, adding of minus beta x cube, and adding of delta sine omega t, which should give me x double dot, right? So there should be a block which adds all these things and will give you this output x double dot, right? So I'll have a block where I have to add everything, right? And it will give me an output. Like the arrow which is going outside of a block is output, right? And the arrow which goes inside of a block is actually a input, right? So I can just write it here. You have a block. Okay, so this should be your input and going out should be your output. Alright? So, okay, so how many inputs do you, output will have one. Whatever you are getting out of this block will be your x double dot, right, as per this equation. So this should be your x double dot. How many inputs do you need for this? 4, right? So for this block you will be needing 4 inputs, okay? So our first input should be x dot, right? And you are multiplying it with gamma. So you are giving a gain gamma, minus gamma to it, right? Okay, we will talk about gain later. First we will just see. Let's keep it here. So you got x double dot here, right? You integrate it once, you will get x dot, correct? So if I put a integrating block here, okay, I'll just write int for understanding now, okay? So once my x double dot goes inside, what will be my output for this? It will be x dot. Is this clear? Right? I am just giving x double dot as an input to the integrating block. It will integrate, so what will it give you? X dot. Okay, so now you have got x dot. How will you get x? Integrating x dot, right? So, okay, I am just putting this as an arrangement because I know in my head beforehand that it's going to be complex, okay? I'll just put x here. Okay, so this is again an integrating block. I'll erase this. This x dot is going inside this block. What will be the output? It will be x, right? So I am getting x out of it. I am giving x dot, here it's going x dot and it's giving me out x. Okay, so now this is also done. Now what do you need? X cube. Right now we are working only on variables. Coefficients we will take care later. So now you need x cube. Okay, for x cube you need a product of x 3 times, right? So you need a multiplication block out there. Okay, so say I have a multiplication block here which do product 3 times. So it has 3 inputs. You can give 3 inputs and it will give you 1 output. Okay, so all the 3 times I am giving x. Okay, so this is also output here. I am giving x. What output it will give me? X cube. Right? So this is a product block basically. Now you need force. Right? So you need it as a sinusoidal source. Some like sinusoidal block you will be needing. So that I'll put here. Okay. So we'll make this all everything there. It's in some form of delta sine omega t only, right? This is your force, right? It's just a generator. Okay, you don't need, you will just put input, you will define your variables in here and it will give a, in the lab you would have seen signal generator, right? It's more or like, it's something like that. It's just generating the signal. With the parameter which you are giving, it's just generating the signal. So you are generating force from here, okay? So now we have all variables and force ready. Now we need gains. right? So x dot needs to be multiplied with minus gamma, right? So from here we can just take x dot, add again, okay, add again minus gamma. So this becomes, the output becomes minus gamma into x dot, alright. Then x needs to be multiplied with minus alpha. So we can just take it here and put again, which is minus alpha, and the output here becomes minus alpha into x, alright. And your x cube needs a gain of minus beta. So you just put a gain here, which will minus beta, and output will be minus beta x cube. Okay. Now you have everything ready. You just need to add all those things and your block diagram will be good to go. So I just need to put it here. You can just put it like this. And one more I will be needing. Okay. So my block diagram is now ready. I am adding all these things. Once you add it, what you are getting? X double dot. And you integrate it, becomes like this. Okay. Anyone has any problem in this? Any doubts in this? It's a kind of loop, yeah. Usually block diagrams will be in the form of loop. Otherwise, how it's going to simulate? Everything has to be connected, right? Okay. So once our rough idea of block is ready, I'll just show you how it is done in output. Okay. So now also one more thing. Now you have everything. How you get the results out of it, right? So if you have worked on experiments, you can use scope. Okay. Scopes to get output, like visualize how the output is. So suppose I want output at x, I want a displacement and I want velocity also, right? So I can put a scope here for displacement. Okay, this will give me x, and one where x dot, at x dot I can put, right? This will give me x dot. Okay. So this will give you the real time plots, scopes will give you the real time plot while simulation is going on. Okay. Now say if you want to save it in the workspace of MATLAB, since I said, right, Simulink you can work through MATLAB, and you want to do post processing in MATLAB. I think in yesterday's Abacus class also it was being told how you can just save your output and use later on, right? Like that you can do here also. Okay. So for Simulink, whatever you are giving to a Simulink, that is called source. Okay, whatever you are giving to the block diagram is called source. So this is also a source. You are giving inside the block diagram, right? When you want to take out something out of the block diagram, you will have to put a sink. Okay. So you want a sink for the workspace. You want all your variables to be stored in workspace of MATLAB while the code is running. So you have to put a workspace sink. Okay. So it basically syncs everything to the workspace. So one sink I can put here for x. Okay. So this will actually save my, you can just name it as workspace sink. This will give me x. Likewise, you can do for x dot also. Okay, workspace sink here. X dot. Okay. So now I think we have covered almost everything which needs to be added in a Sorry? Yeah, so when you run simulations in Simulink, suppose if you want to do post-processing of your data, whatever is being generated in Simulink later on, there are different ways in which you can plot dynamics of a system, right? You can plot phase portrait, time histories, or kinetic energy, potential energy, and all will be plotted through the phase variables, right? X and X dot. So you want them to be stored back to the MATLAB. So MATLAB's workspace if you want to store. So Simulink, whatever it goes out of the blocks are called sinks. Okay, whatever goes inside the block are called source. So say force you are giving, right? You are generating force. So this is a sort of source. Now they have generated, suppose the simulation is run here in Simulink and X and X dot is being generated. Now you want to take it out to the workspace. You want to save it there. So you need to put a sink. Okay, so you can just put sink blocks, workspace sink blocks. One you can put over the output X and one at output X dot. So that will give you that will save your these simulation variables in workspace, MATLAB workspace. Okay, I'll tell you how you can access it there. Okay, so first thing is, suppose you have MATLAB open. You can just type Simulink in here and it will open for you. Okay. Okay. So you just need a blank model. So we create a model. Actually this block diagram you can generate directly in the Simulink, but this is the best way. First have a rough idea of what all blocks you need, because this is just a simple say 4 terms equation, right? Sometimes these equations comes out to be very complex and your block diagrams comes out to be very complex. So that if you don't have a mental arrangement of where the blocks are, then it becomes very difficult to keep a track of which block is connecting to which block, okay, which is input, which is output. So it's always better if you can just have a mental picture of how your block diagram is going to look. Then it's very easy in Simulink. You just have to introduce block, place it according to this and you're good to go. Okay. So once you open Simulink, open a blank project, this window will appear. Now you need to put, we'll go just like how we went in this block diagram. Okay. So first we need a summation block, right? So there are two ways. Either you can go to library browser, click it and search here. Okay. The other way is just double click on the workspace and here the blocks will come. Okay, so you need an addition, just write add and it will come. Okay, so this is 2 inputs, right, and 1 output. You need 4 inputs, right? Just double click in here. So list of signs you need, instead of 2 you need 4. Just add 2 more, that's all. Okay. So now it has 4.
But it could be also with negative sign.
Yes, yes, yeah, right, sir, yeah, yeah.
Plus means positive.
Yeah, like how I did all positive, it can have negative also. Right now what I am doing is, I am giving negative gains, okay. That actually reduces the confusion, but you can change it here as well, okay. So we will just place it according to that. So we will place it somewhere here, okay. Next are the integration blocks that we need, right. So I will just double click, put integrator. So it's this is integrator block, okay. So one integrator block I need somewhere here and one more integrator block. Another integrator block I need somewhere here, right. Just to clear out the confusion, I will just name it as, this is the integrator for X dot, okay. So I can just write V also, right. X dot is velocity. For this is for X, so I will write it X. Fine. What else do we need now? We need a product multiplication block, right? Yeah, so multiply block. Here again, no, it's again, okay, wait. I think it's product. So here I need it 3 times, right? I can just put like this and it will work. So see, now it has 3 inputs and 1 output. Okay. So this is also done. Okay. So this is for our x cube. I'll just write it as like this. Okay. This is for, this will give me x cube. And then what do we know? What do we need? We need a signal generator, right? We need a, yeah, see, sine wave, it's a source, right? So we need a sine wave. Sine wave will just give values of delta. Okay, I'll define these values according to how it was defined last time in the MATLAB. Just a minute. Yeah, so we have gamma is equal to 0.2, alpha we have -1, beta we have 1, delta we have 0.3 and omega we have 1.2. So you see here the amplitude is actually delta, right? It's delta sine omega t. So delta's value is 0.3. Okay, bias we don't know, we don't need to give. Actually this is the output, right? Okay. So yeah, so delta is 0.3. Okay, so it's in this form, right? Delta, you need sine, frequency t, phase is also 0, bias is also 0, right? And frequency is 1.2. Okay, so our source is like, these are the parameters we need for our source. So it's done, right? Then what else do we need? We need gain blocks, right? So one gain block we need somewhere here. Okay. So this gain block is actually alpha, minus alpha, right? I'll just write it here. Minus alpha. Okay. Then you need one gain block somewhere here as minus beta. Then one gain block for the velocity somewhere here. Just a minute. You need one gain block somewhere here, okay? I can even rotate it actually. Okay, for now it's fine. So one block you need here, and this should be with the, for the velocity, right? It's minus gamma. Okay. Now we need to give values in there, right? So just double click it. So you need, your alpha value is -1. Alpha is -1, so minus alpha would be 1. Okay. Yeah. For minus beta, we have -1. For gamma, we have minus 0.2. Okay. Okay, so gain is also given. So that's all. Now we'll connect. So first connection should be from here to the velocity, right? So this will give, suppose this is actually giving me double dot of x, right? So I'll just write d dot of x. This is giving me acceleration, right? Okay. Here also, to avoid confusion, I'll just write dot of x. Okay, and then we need from x dot, we need to input for x, right? You just have to drag it. It's more like Microsoft Paint once you know the blocks. Okay, so now we have x double dot, then we have x dot, then we have x, right? Then we need x cube. So you can just put it here. Sorry. Yeah. From here you want here, that is 1x, then again another x, and then another x. So this actually gives you x cube. Okay. So now we have x double dot, x dot, x and x cube. Now I will give gains to these values. So x needs to be multiplied by minus alpha. Okay, x cube needs to be multiplied by minus beta. And your dot x needs to be multiplied by gamma. Okay. Now we need to add all these 4. So we just okay. So this is my governing equation for Simulink. Okay. Now I will add scope, as I said, right? Workspace and scopes. So just again double click, write scope, it will give you scope. See, as you can see, it's showing Simulink / sinks because you are taking an output out of the Simulink block. So it comes under sync. Okay, so this scope is for x. So this scope is for x. Oh, okay. So I'll just write it as output x. And we need another scope for x dot. So this is for out dot x, output of dot x. Okay. So this one we need for x. So it should connect here. This is the output for x, right? And one we need for x dot. It should connect here. Okay. Does anyone, everyone got this? Why I have put it here? Does anyone has doubt in this?
Yeah, I just want one comment because sometimes it is also possible to just to click on this library browser.
Yes, sir, I mentioned that.
If you click on that,
you can search it here, like.
But it's it should be some kind like symbols of these blocks, but you can also collect by mouse, I'm not sure why it is not present here.
No, sir, it comes.
Yeah,
you can just drag it. Suppose you want integrator, you can just drag it here to the library.
You can track each one which you need.
That also is possible. See. Okay. You can drag any operator which you want.
This is a comment,
Yeah, so it can come. Okay. So now we have scope also, but these scopes will not store your data. It will just show your data. Okay. I think if you know doing experiments, if you have an experience in doing experiments, you would know what scope does. Okay, so it's exactly the same. But if I want it to be stored, I need a workspace sync. Okay, then I'll just double click and write, see, to workspace. I need a sync that can store it to the workspace. Okay, so it's like out, sim out. Okay, I can just rename it as X out. Okay, and I need a format, it needs to be structured with time. Right, so for corresponding like time also it will give. Okay, so this is for X. Okay, so let's just and one I need for velocity, say. So again I will write workspace sync and I will get it. Okay, so this I need as dot X out. Okay, so now it is complete. Okay, now you can just here, as you can see in the bottom corner, it's written variable step auto, right? So once if you run this simulation right now, it will because even when we did in MATLAB, we had defined time steps, right? We have defined at what time step you need your simulation to be run. So here again, as you can see here also up, right, stop time is here 10 seconds. Okay, I can modify it to 100 seconds, 200 seconds, anytime. So it will start from 0 and end at 100 seconds. But we have not defined any time step as for now. So it will take any variable time step, and it can take any solver also according to its convenience or according to the algorithm already like default solver. So just in case if you need to change those, you can just click in here and go for settings. Okay, so you see here solver is also automatically it's been selected, so you can select any other solver. Last time we did it through OD45, we can select that also. Okay, and you want a fixed step, not a variable step. Okay, so you can just give a fixed step time as well. Suppose you can just give anything 0.001, anything that you want to give. Okay, and now you see it has changed to fixed. Oh, is it? Okay. Oh, sorry. You can change it to ODE4. Yes. Understood? You can go to here, just click it, go to the settings, and you can change. So now this is done. Now you can save it and you can run it from here. Okay. So I will show you. Yeah, also for the face portrait, now this I have already made for your understanding. Okay, you can also get a XY plot. For that, you just need to type XY plot. So you will get XY graph. Okay, so this is also an output, but you see you need two inputs. One is for X, another is for Y, right? So X is for face portrait. Say if I want to generate a face portrait. Okay, so for face portrait my X is X, I mean like displacement, right? Oh, sorry. Yeah. So I can just make X connect here. Okay, and Y is my X dot, right? So this is my X dot, so I will just connect it here. So this will give me a direct like real time XY plot. So since my x is displacement and y is velocity, it will give me a phase portrait. Okay. So now we'll run it. So I have already made a like block diagram, which is better looking. So I'll just run this. I have put the exactly same parameters here. Okay. So I'll just run it for you. Also here, if you want to see your simulation going on, you can change your simulation pace also. Okay. So you can like it enable it or disable it. So right now I am enabling it, and per time I have I changed it to 20 seconds. Okay. So if I run it like this, you can see the scopes will come. Yeah, so you see, you can see it in the scope how your displacement time history and velocity time history is generating as the simulation is going on. Okay. Also, if I now double click phase portrait, okay, I think I should have opened it before. Okay, I'll just run it again. I think there is some problem in this. It should give phase portrait.
Maybe not run, just one step forward, yeah, or run maybe.
Oh, run, I have been running, sir. Like.
From here, yeah, continue.
Yeah. Thank you, sir. It came. Yeah, so like you can even directly get. So these are Simulink results. You can either save it from here, but as you can see in the block diagram, we have taken out x and v, okay, displacement and velocity in the workspace. So in the back end, since it's running in MATLAB only, right? So in the back end, you see the variables are being stored in this 1x1 simulation output. Okay, so you can just fetch out those variables. So here you can see this is time, output x, right? We had saved it with this name, variable name x. So you need time from that and you need the signal values. Okay, so it doesn't know, it is just storing it as signal values, right? So but the name library like which you have saved is like x out, right? So from x out you need time and signal values. So that will give you displacement time history, right? Now from for the phase portrait you need displacement, right? So from x out you need signal values, and also from v out you need signal values. So this will give you the phase portrait. So you can run it here as well. I think there is some problem. Just a minute. Yeah, it didn't run actually here. It got clear up.
We can also check what is the stored variable.
Yeah. So that is actually like, it did not run completely. Now it is stored, I guess. I'll just check it. Yeah, so you see, like you similar plot, right? Like what you got here as time history and phase portrait, you can store those values and get it like this. It's actually same if you just, yeah. So you'll get exactly same plot. Like you can fetch it later on, you can save it in your workspace and you can get it, okay. So that's about Simulink. You can use your own governing equations and all. The main challenge lies in developing this block diagram. Once you have it, then it's easy. Okay. So anyone has doubt in this? Yes? you are doing it now. Can we discuss it after the session? I'll help you out. Any other doubts? Okay, okay, I'll discuss with you afterwards.
I have also comment, but you can have such a Simulink code on the disk, but you can still work with MATLAB. You can call for the Simulink from the MATLAB, and you can plot afterwards. You can plot some results. Yeah. So you needn't to go to this diagram, but it should be tested before. Yeah. But if this is working, then you can start from the level of the MATLAB, and you needn't to look to the disk, and only if you want to make some correction in this diagram, yeah, you can do this.
Okay. So that's about Simulink. I'll discuss with this after this session if anyone has any problem and doubts in this. Okay. So the next part is simulating piezoelectric cantilever beam using energy harvester. Okay. So in last session of MATLAB, we did simulation on this spring mass damper system. Okay, that is without energy, like piezoelectric patch, right? So how do we need to simulate it once this electromechanical coupling coefficient comes into picture? Okay, it's not very much different from how it is for like without the piezoelectric patch. Just how you write the equations, how you define your state variables, that's where the difference lies. Okay. So first, before starting with this code, I'll just explain how to write state space equations for a piezoelectric beam. So I think it's been covered in almost every session that the governing equations for a piezoelectric energy or any energy harvester, when there are two different transduction methods like a transduction process is involved, then you have some coupled equations, right? One equation will correspond to the mechanical part of the system and other equation will correspond to the say electrical part of the system. Okay. So for piezoelectric energy harvester, this coupled equation looks in like here I am considering just the linear case. Okay. So it will have the same governing non-linear terms. This I think everyone knows, spring mass damper. Suppose if you have a beam, a cantilever beam, okay, with some tip mass. Okay. So I think if you guys are from mechanical background, you would know how to find out equivalent stiffness of a continuous beam, right? You will have bending equations, and with that you can just, with the help of deformation, right, whatever maximum deformation, you can find out the equivalent stiffness of the beam. So this term can be found out. Likewise, equivalent mass also can be found out, and stiffness, right? And damping is somewhat tricky to find out, but there are some standards like 1%, 2% structural, like depending on different structures, you can just consider the damping values, or you can find out experimentally as well, okay, because it's just the loss of energy involved in the system. So there is not just one factor involved in the damping, but there are multiple factors. So it's not a straightforward relationship through which you can find out damping. It's a bit tricky part. So usually we consider some standards for different structures, like what damping could be. Okay. So this is one of the ways. There are very different ways through which you can, so basically your cantilever beam is a continuous system. Okay. So your this displacement actually will be a function of both your space. So it's x, right? So say suppose you have a displacement like this. Okay. So this will be a function of both, say this is x, right, x direction. So it will be a function of both space and time, right? But in order to simplify our system, we try to reduce the system as ordinary differential equation. We try to use, so if you are using lumped parameters, these are called lumped parameters, okay. So these lumped parameters can be found out by using different, so this is lumped parameter analysis. So there are multiple ways in which you can solve a continuous equation. So reducing it to lumped parameters is one of the ways, okay, so which is what I am going to show here. So this is just your physical equation, which I think now everyone is familiar with. Then you have a coupling term because of the, since I am talking about piezoelectric energy harvester, there will be a coupling term which will be theta into V. Here your V is voltage, okay, and theta is your electromagnetic, not electromagnetic, electromechanical coupling coefficient. Okay. So basically it is relating the electrical and mechanical part in the system, right. You have this voltage term because, so what this theta is doing, it is actually giving some physical meaning to your voltage, so that it can be like it is actually giving you the force term. When you multiply theta into V, it is giving you a forcing term for this equation, okay. So which is equal to again F sin omega t. Okay. So this is the mechanical part of the equation. The electrical part of the equation is V by RL. Here your RL is load resistance. Okay. So V by RL plus Cp V dot. So your Cp is capacitance of your piezoelectric patch. So what happens, this theta, right now we do not have the time to dig deeper into the derivations, but this theta actually depends on the electromechanical properties of your piezoelectric patch, whatever piezoelectric material you are using. So it depends on the electromechanical like coupling, because piezoelectric is a transducer, right. So it will have this coefficient. It also depends on the geometric parameters of your material, piezoelectric material, right. So sometimes while defining theta, they would define it with a sign negative beforehand, okay. So like that depends on the definition that you are giving. So theta also again it is a derived quantity, okay. It is not a material property straightforward, it is a function of the material properties and the dimension, like volume of the system, like patch you are using. So when you define this theta, if you are using negative sign beforehand, then this might change. That's what it is. It depends. If it is included, then the sign is switched. If it's not included, like you have to see. That comes out of the derivation once you do it, okay. This is just the final equations we are talking about right now. Okay. So then minus theta x dot is equal to 0. So this is the electrical part of it, okay. So here you can see for our mechanical part we have two states variables. Okay. So for mechanical part you have two state variables, which is first is x, second is x dot, right. This is what we covered in the last class also. We defined two equations and two state variables. Because of the electrical part you will have a third state variable, which is voltage V, okay. So now we have to define equation such that integrating those equations will give you these three variables, okay. So say I name this as x of 1, this as x of 2 and this is x of 3. So I have, suppose, okay, for the like it might be confusing. I'll just rename it as u for now. Okay, so my x is a vector which will contain x of 1, x of 2, x of 3, which will be equal to u, u dot and v. Okay, u and x are not different. I have just renamed it to avoid confusion here. Okay, so I have to define it for now. When you write a equation in state space form, you write it in the differentiation of your state variables, because when you write in the differentiation differentiation of these state variables and put it in the solver, it integrates the equation. So once it integrates it, you will get these values, right. So if I want to write this set of equation in state space form, how will it be? My x of 1 is x, x of 2 is x dot, and x of 3 is v, right. So my x of 1 dot will be my x of 2, that is my first equation, and my x dot of 2 will be minus of 1 by m. C, my x of 2 is x dot, so I will write it x of 2 plus k x of 1 plus theta x of 3 minus f sin omega t. Okay, this is my second equation, and x dot of 3 will be, you take everything to the right hand side, so it will become minus 1 by Cp. So your V is x of 3, so it will become x of 3 by RL minus theta x of 2. Right? Are these equations clear? So this is how you write your equations in state space form. So when you integrate these equations, right? So after integration, for integration you use numerical techniques, right? So for MATLAB you have ODE solvers, and then you get x of 1, x of 2 and x of 3. Okay, clear? So same thing now we will do it in MATLAB. So as you can see, this is the code for piezoelectric cantilever beam energy harvester. So first we are just clearing out the workspace, clearing out the command window and closing all the opened windows to avoid confusion. Okay, then we are defining the system parameters, right? So what all do we need? We need M, we need C, we need K, we need theta, we need Cp and RL. RL here I have written as R. Okay, so R is the load resistance of the system. Then excitation parameters I am giving force as like 1, amplitude, and omega as 100 radian per second. Okay. Now I want to run my simulation for 5 seconds. Okay. As you can see here, I have not defined the interval. I can just define it as 0.01. Sorry. Seconds. Okay, and these are the initial conditions. Now you see you have 3 state variables, right? X, x dot and v. So you have to define 3 initial conditions. Okay, so now again we are defining ODE function. Here I am giving these equations as I have written, right? So my x1 dot I have to, so you don't have to write x1 dot is equal to x of 2. Once you put it in ODE solver, it automatically takes the first equation as the differential equation for the first variable, second equation as the differential equation for second variable, likewise, okay. So I am just defining those values, what is x1 dot, what is x2 dot and what is x3 dot here, okay. So you can see, so the first equation is my x of 2, second equation is 1 by m, okay, I have taken out negative sign out here, but it's same, okay. And third equation is minus 1 by Cp, 1 by r into x of 3 plus theta into x of 2. I think that should be negative. So once you define set of equations, then you just solve it using ODE solver. As I mentioned, there are different ODE solvers, okay. So you can just check in the documentation, and as per your need you can change these ODE solvers. You can even write your own solver, that is also possible in MATLAB, okay. So once you get it, you can see here, right, your first column of the result that you will get output as capital X. You are defining your output as capital X, okay. It will have 3 columns. So first column will be x of 1, which is your displacement. Second column will be your velocity, okay. And the third column will be your voltage. So you can just extract it out that way, okay. Once you do that, like we have just plotted, and also you will get a vector, here you see you will get a vector of time also, t, and corresponding x. So once we get all these results, we can just plot the results. We can plot time history, velocity history and output voltage history. You can even calculate power using load resistance V square by RL, right, that also can be find out, okay. So I will just run this, yeah. So you see, you have displacement time history, velocity response and output voltage response. So this is how you simulate energy harvesters in. So if you are using electromechanical equations, the procedure will be same, just as these set of governing equations will change, your parameters will change, but the procedure will be exactly same.